Let's take a look at computing some more arc length. So again, I am just projecting our formulas for arc length. So if we have a function at y as a function of x from a to b, then we find the arc length by integrating from a to b the square root of 1 plus the derivative of the function squared with respect to x. Now, of course, if the function were x as a function of y, g of y, we can do the same thing, take the derivative of the function, square it, add 1, take the square root, and integrate across the bounds from c to d. So if you haven't written these formulas down, make sure you write these formulas down because we do need to utilize these. But now let's take a look at an example. So let's suppose we want to find the arc length of the curve f of x equals 1/3 x to the 3 halves on the interval from 0 to 60. So we know we're going to use our arc length formula. I have it copied down here. But I prefer, before putting it in straight into the integral, I prefer to simplify this expression under the square root first. And then when I go to the integral, I won't have much more simplification to do, and I can get right into the integration techniques. So let's go ahead and think about if I have f of x is 1/3 x to the 3 halves. Then when I take the derivative, just using my little power rule here, 1/3 times 3 halves x to the subtract 1 there, we get 1/2, and so this ends up being just 1/2 x to the 1/2, which of course is just 1/2 square root of x if we prefer to write it in its root form instead of fractional exponent form there. Now, again, back to that idea of I like to get this all simplified before I plug it into the integral. So you will see in my work, I will do this work kind of off to the side, a little bit of side work over here before going into my integration. All right, so then this, I need to take that derivative, square it, add 1, and take the square root. So notice when I square that, I get, it's kind of convenient because I just get 1/4 times x because we're squaring a square root. So that just becomes x to the first power. And then I'm going to just keep simplifying this root. It does simplify a little bit nicer. I can just find a common denominator, and the common denominator is a perfect square. So this becomes the square root of 4 plus x over 4, but that's the square root of 1/4 times the square root of 4 plus x, and that is simply 1/2 square root of 4 plus x, and that's really nice. That's simplified down very nicely. So now when I compute the arc length, plugging into my formula, I'm going to be integrating from 0 to 60 of 1/2 the square root of 4 plus x dx. And this is going to, I'm going to go ahead and zoom in a little bit here. This is going to involve a little bit of substitution because I've got that 4 plus x, I have that function under the square root, so I'm going to use substitution here. U is 4 plus x, so that makes my du simply 1. It's du dx equals 1, but I'm going to separate the differential, and so that becomes just 1 times dx, or du equals dx directly. So that substitution is really nice, simple. We're going to make that substitution. We get 1/2 u to the 1/2 du. Here, the bounds were in terms of x, and I'm going to go ahead and switch those over in terms of u so that I don't have to go back in terms of x on this problem after I integrate. So since u was 4 plus x, 0 plus 4 makes 4, or 4 plus 0, and 4 plus 60 makes 64. So I'm going to change my bounds. I'm going to keep going. I'm going to integrate. Nice little power rule here for the integration. So this becomes 1/2 u to the 3 halves times 2/3, because I'm dividing by 3 halves, and then evaluated from u equals 4 to u equals 64. This is 1/3 u to the 3 halves, evaluated from u equals 4 to 64. And this is going to come, I'm just going to come down here. This is going to become, oh, it's going off the screen. Sorry about that. Come down here. This is going to become 1/3. I'm going to pull the 1/3 out in front of the whole shebang here. And this is going to become 1/3 64 to the 3 halves minus 1/3 times 4 to the 3 halves. And this problem was definitely cooked up kind of nicely let's see, what was it? It was from 0 to 60. Get the problem up on the board there at the top. This problem, I mean, it was, what I mean by it was cooked up. I just am looking at those bounds that we're plugging in, and it's really nice because 64, when you raise it to the 3 halves, you're taking the square root of 64 and then cubing it. So this actually becomes 1/3 8 cubed. The square root of 64 is 8. And then 1/3, the square root of 4 is 2 to the third. And so then we've got 512 over 3 minus 8 over 3. And then that becomes nicely 504 divided by 3. And 504 divided by 3 is 168. And that's in units because it's a length. So this is my arc length here. And my arc length is 168 units for this problem. Let me go ahead. I'll see if I can get it all. I'm pretty close. We almost have it all on the board. We're getting the next example there too, but there we go. 168. And so that worked out really nicely on that one. So that is the length of that curve, 168 units from 0 to 60. I'm going to squeeze one more example on this video. Let's take a look at this one. This is the arc length of the curve x equals y to the 4th over 8 plus 1/4 y squared on the interval for y's between 1 and 2. So clearly on this particular one, we are utilizing our other variation of the arc length formula because we have a function of y. We have x given as a function of y. So we're going to do it the same way, but we're going to be working with a function of y instead of a function of x. And I will, again, you will see me do kind of my side work. I like to work with, I'll kind of come over here, my side work. I like to get that simplified as much as possible. I like to get that expression right there simplified as much as possible before I go and I put it back into the integral. So let's go ahead and do that over here. So if my function x is y to the 4th, and I'm going to write it as 1/8, excuse me, 1/8 y to the 4th plus, and I'm going to write this as 1/4 y to the -2nd because we're going to be applying our power rules to take the derivative, so I think it'll help to see it that way. And we want to find the derivative, so the derivative of x with respect to y. We're going to get 4/8 y to the 3rd minus 2/4 y to the -3rd, which becomes 1/2 y to the 3rd minus 1/2 y to the -3rd. All right? So that's the derivative, but remember now I need not just the derivative, I need to take the derivative, I'm going to square it, I'm going to add 1 and take the square root. And so to get that simplified, before we plug it into the integral, let's expand out that interior of the root. So we get 1/2 y cubed minus 1/2 y to the -3rd, and we're going to square that. So I'm going to expand that out. I'm going to come down here. I'm going to do some algebra. I'm going to bring that more up to the top of the screen. We're going to do some algebra here. This is going to become, we still have that 1, and then we're going to expand that out. And so when I expand that out, remember I'm multiplying that by itself. And so when I do that, I get 1/4 y to the 6th. I get minus 2 times, now I'm going to multiply those two things together, so it's 1/4 y to the, when I multiply, so the middle term, I'm utilizing that formula where the middle term is twice the product of the two, if you think of this as being a perfect square, like a plus b squared. So I'm multiplying those two together and then doubling it so that I'm using that formula right there. I'm verbally saying it, but I'll write that out there too. So when we multiply those two together, we get the negative, we get 1/4, I already put the negative out in front, we get 1/4 y to the 0, because y to the 3rd times y to the -3rd becomes y to the 0, and then I get 1/4 y to the -6th. So going through that all, that was the expansion of that binomial squared, and I'm going to continue to simplify. So this is 1 plus, we're going to have 1/4 y to the 6th. Now this ends up becoming just 1/4 because y to the 0 is 1. So then we get minus 1/2 plus 1/4 y to the negative 6. Now I do want to just highlight that part. We're going to add that 1 to continue to simplify, but I want to highlight that and notice that that is this expanded. That is those two terms squared. And so just kind of keep your eye on that because something really similar is going to happen on the next line. We're going to add the 1 and the minus 1/2, so that becomes a positive 1/2. And I'm going to write it like this: 1/4 y to the 6 plus 1/2 plus 1/4 y to the negative 6. And this is a perfect square. So that's why I highlighted. Notice how similar it is to the piece of the expression I had highlighted right above. These two are so similar. They are similar, perfect squares. And that means that I can actually factor this because it's a perfect square and it's going to factor very much like it was up above, right? We expanded that, but then we added that 1 and we got almost exactly the same thing, but with a positive middle term instead of a negative middle term. So this factors into 1/2 y to the third plus 1/2 y to the negative third quantity squared. And look at that. Those are very similar perfect squares, so we can see those patterns right there. So that's why I wanted to highlight it. We can see those patterns happening right there. Okay, so we factored that, and now we have a perfect square under the square root. You can see now why I might want to do this work outside of the integral, because now I'm going to get this nicely simplified, and look at what's going to happen. That, when we take the square root of that perfect square, we get the absolute value of what's inside, which is 1/2 y cubed plus 1/2 y to the negative third. It is an absolute value, but remember that y is between, I believe it was 1 and 2. I have to look back up here. Yeah, notice here that y is between or on the interval from 1 to 2. So y is always greater than 0 here, which means when we cube it, or when we drop it to the denominator and cube it, that this quantity is always positive. So we can actually drop the absolute value, and this is 1/2 y cubed plus 1/2 y to the negative third. Okay, so a lot of algebra right there, kind of also thinking about the bounds when we took the absolute value. And now we can actually find the arc length. So the arc length is simply going to be the integral from 1 to 2 of what we just found right here. I'm going to circle it. We just figured out that the square root of 1 plus dx dy squared is equal to this nice simplified version. So the arc length has to be the integral of 1/2 y to the third plus 1/2 y to the negative third with respect to y. Now I'm going to zoom in there so we can actually do that calculation. It's not tiny on the screen. So when I integrate it, since I've already done all the simplification, that's why I like to do the simplification off to the side. Get all my simplification done, then bring it into the integral, and if needed, apply any integration techniques. But this one's just going to be a basic integral, basic power rule here. So this is going to become 1/2 y to the fourth over 4 plus 1/2 y to the negative second over negative 2. And we're going to evaluate that from 1 to 2. All right. And then just keep going with our simplification here. This is going to become 1/8 y to the fourth minus 1/4 times 1 over y squared, evaluated from 1 to 2. We'll go ahead and plug in. And I think at this point I'll speed it up a little bit, and we'll just calculate this. All right, so we ended up with 33 over 16 units of arc length, and I will zoom out. so I can get the whole example on one screen there for you if you want to take a look. So again, remember, I like to do my work off to the side because a lot of times with these arc length formulas, since we have to take a derivative, square it, add one, and then take a square root, there is a significant enough amount of simplification. I'd rather do that before I pop it into the integral, and then I can pop it into the integral and use my integration techniques.